Hello, my name is Yesdalil Aizenov, and I'm a third-year PhD student at the University of California in Merced, working with Dr. Florian Russo. In this presentation, I will present our new query optimizer called Compass. That is a lightweight yet efficient query optimizer for in-memory database systems. So, in general, a query execution plan is optimized before it is passed to the actual execution. A query optimizer includes two important components that are cardinality estimation and plan enumeration models. The cardinality estimation is the most influential component that the query optimizer uses to find an optimal plan while enumerating and evaluating many different plans. The cardinality estimation has been studied for several decades, and there are quite a few methods that have been proposed to tackle the problem, trying to get very accurate estimation or improve the existing results. However, even small misestimations can confuse and mislead the plan enumeration algorithm, leading to suboptimal plans because it heavily relies on the cardinality estimations. Let's consider one example query. In each query, the query is typically represented as a graph where the nodes are connected based on the joint predicates. In this example, we see that there are 5 input tables in the query, thus there are 5 nodes connected with 5 edges. The plan enumeration algorithm relies on accurate cardinality estimations in order to figure out a better join order with the minimal cost. However, the enumeration algorithm can be easily misled by over and underestimations. From the figure, we can see in each different database system, its optimizer relies on its cardinality estimation method, therefore providing a different plan. Let's now review the existing approaches. There are 3 main existing approaches. All 3 have their own advantages and disadvantages. The synopsis-based approaches that are, for example, histograms and sketches, have a very good accuracy on simple queries and they are easy to process and implement. However, in the presence of many joint predicates and data correlations, the accuracy and scalability problems arise. There exist also sampling-based cardinality estimation methods that are agnostic to data and workload changes. However, the overhead greatly increases in estimating a large number of table joins. Therefore, it is difficult to scale up the methods. Recent approaches based on machine learning methods and deep learning methods provide very appealing, accurate performance results in the cardinality estimation. However, the methods are typically not agnostic to data and workload changes, requiring model retraining, where the training phase needs a large number of training set queries. Considering the limitations of the existing approaches, we propose a new query optimizer called Compass. Compass is based on a single types of synapses, that is sketches. The sketches are compressed representations of a streaming data requiring a small memory space. The sketches can be built fast and in online fashion and easily handle data changes. There are several types of sketch techniques invented to target different streaming data problems. Among them, there are types of sketches that are applied in the cardinality estimation problem, like AGMS and fast AGMS sketches. Compass is based on the fast AGMS sketches. And the existing sketch-based techniques that are applied on the cardinality estimation problem have one major disadvantage that stops them to be applicable in the query optimization. Those methods are not scalable to capture the multi-way joins. In order to capture the multi-way joins, a separate sketch for each join and join combination is required to be built. And also, in the presence of selection predicates, the accuracy also suffers. In Compass, there is only one sketch per join attribute built during the selection pushdown, which makes the optimizer agnostic to arbitrary selection predicates. In addition, Compass builds the sketches per query to adapt to the data changes. And individual sketches are incrementally composed in order to estimate any join combination during the plan enumeration phase. Since by nature the sketches are highly parallelizable, we can estimate large number of join cardinalities in a larger plan search space. Now we will illustrate the architecture of Compass. For each query, we build a new set of sketches that will capture recent data changes. For each base table, we push down the selection predicates before the enumeration phase starts. This allows the optimizer to be agnostic to arbitrary selection predicates. And as a byproduct, we build our fastest image sketches. As you can see, this is an architecture that is different from the canonical query optimizer architecture. And also, for very large tables, the sample data can be used to build the sketches in order to further speed up the sketch building time by also controlling the estimation accuracy. Once we build our sketches per join attribute in the plan enumeration phase, Compass starts incrementally composing the sketches in order to estimate any join combination cardinalities. And now we show how the sketches are built, and then we show how they are used in a two-way and multi-way join cardinality estimations. In the example for table K, we built a sketch of 4 buckets using 2 layers of hash functions. First, we identify the bucket number by using the first hash function. And then using the second hash function, we decide whether to increment or decrement the count in the bucket. Table K joins with table MK in order to capture the correlation between the tables. The same hash function is used to build the sketch for the MK on attribute keyword ID that joins with table K. And since table MK has a separate two-way join with another table T, we build a sketch for the table T using a different hashing. And then with the same purpose, to capture the correlation between MK and T, we use the same hash functions that were used to build the sketches for T. As a result, we built another sketch for the movie ID attribute in MK to capture the correlation between MK and T. All the sketches are built based on the tuples that satisfy the selection predicates. Now we show how the sketches are used in a two-way join cardinality estimation. In the two-way join cardinality estimation, the individual sketches are used. To estimate the join between K and MK, we sum the element-wise multiplication of each bucket between the two sketches. In the example, we estimate the cardinality as 7, and the true cardinality is also 7. Respectively, to estimate two-way join between T and MK, we use the same estimation function. And as a result, Compass estimates the join cardinality between T and MK as 7, where the true result is 6. Let's now consider a three-way join scenario. In order to generalize the optimizer for multi-way join, we need to compose the two sketches in MK. In our work, we showed multiple ways to compose the individual sketches to capture the tuples that are connected with all the joining tables. You can read more about the methods in the paper. Merging the individual sketches in tensors is not a scalable approach because as the number of joining attributes increases within the table, the estimation time and the memory consumption increases as well. Therefore, we use an alternative way of merging the sketches that produce a single merge vector based on the inclusion principle. The intuition behind taking the minimum in corresponding to bucket values from both sketches of MK is that the number of tuples that connect with all the joining tables is at most the minimum of the corresponding two bucket values. Therefore, the estimation for multi-way join is the summation of all element-wise and multiplication of the participating sketches. In the example, Compass estimates the join between K, MK, and T as 8, where the true result is 4. Now we show how the sketches are integrated in the plan enumeration algorithm. In the same query join graph, where there are 5 nodes with 5 edges, we estimate first two-way joins by using the individual FastHMS sketches. Compass chooses the join with the smallest estimated cost. In this case, it's tables K and MK. After, Compass greedily keeps choosing the next joining table with the smallest estimated cost by composing the individual sketches as demanded. So in this example, Compass chooses K and MK, and then it chooses to join CI, then the node N is joined at the end. In each decision, Compass estimates joins with the adjacent node that is not in the plan. In addition, the search space can be large since the estimation function is highly parallelizable and the estimations are memoized as well. For example, the search algorithm can be launched from each node in the graph. Now we show the experimental results. In the experiments, we evaluated Compass from 5 angles. First, we evaluated the cost of the plans generated by Compass based on the sum of intermediate joint data sizes. Second, we compared the execution times of the plans against 4 other well-known database systems. We execute all systems plans on the common ground to be isolated from the execution engine type. We use PostgreSQL and DBMS-A as common grounds. Third, we evaluated the performance of Compass on the entire join order benchmark. Fourth, we measured the overhead of Compass incurred in the building of the sketches during the selection pushdown. And lastly, we compared the cardinality estimation accuracies against the state-of-the-art query optimizer methods. Our experimental setup is the following. We used an IMDb dataset that includes 21 tables where the largest table has 36 million tuples. We used join order benchmark as the workload containing 113 queries, including the complex query that contains 17 tables with 28 join predicates. We also showed that the results according to the query complexities. We grouped 113 queries into 3 groups according to their complexity, that is the number of join predicates. Lastly, we prototyped Compass in a GPU-based open source database system called MapD. First, we evaluate the quality of the plans generated by the systems, including Compass. In evaluating the intermediate data cardinalities on the entire workload, Compass shows better cardinality reduction results. And in presenting the result based on the query complexity is also interesting to observe. Compass shows similar or better results in complex queries, including 10 or more join predicates. In the next experimental result, we explored whether this cardinality reduction translates into faster query execution times. It is explainable that besides the intermediate join data size reduction, the execution engines also play a major role in the query execution time. Therefore, we executed the plans on the common database systems with the same configurations. So in the next experiment, in terms of measuring the execution times, Compass shows similar results, which makes Compass as a new alternative query optimizer that provides good enough results. From the results, we see that the cardinality reduction doesn't always translate into fast query execution times. It is because the reduction size is not large enough to overpower the hardware influence. Looking at the performance based on the query complexities, Compass shows similar or better runtime results in the complex queries with 10 or more join predicates. Now let's see overall workload performance of Compass. In the overall workload performance, Compass shows relatively the best total execution time compared to 4 other database systems. We also compared Compass with MapD's plans on MapD's own execution engine. In this scenario, Compass also showed significantly better results. In our next experiment, we measured the overhead incurred in the selection pushdown based on GPU and CPU-based engines. The overheads are at most 1 second in the GPU-based engine and 10 seconds on the CPU-based engine. These overheads become insignificant in the complex queries compared to the overall query execution time. We also note that the prototype of Compass can be further improved using more sophisticated parallelization techniques. Next, we evaluate the cardinality estimation accuracy for Compass. In terms of the accuracy, we evaluate the misestimations of Compass by computing the ratio between estimation and the true cardinality results. As a result, Compass starts significantly misestimating only after 6 weight joins. We believe estimating smaller joint sizes is more important, therefore Compass shows better overall performance. We also compared Compass against different approaches based on the Q-error metric. The results in the figure, that is estimations for two-way joins, shows that Compass has similar performance. For more detailed information, please take a look at our paper in the repository. To summarize, Compass Optimizer, we say, is a lightweight query optimizer based on a single synopsis type fast HMS that can fit efficiently in the cardinality estimation problem and join ordering problems. We showed how the existing fast HMS sketch technique can be generalized to multi-way joins. We also showed how the sketches can be efficiently integrated in the query optimizer. From the practical evaluation, we evaluated the following. Compass shows better cardinality reduction in the chosen plans. Compass also shows comparatively decent execution times. And in the join order benchmark, Compass performs better in terms of overall runtime. And also, Compass incurs either relatively small overhead or provides better execution plans with small execution costs. In terms of cardinality estimation accuracy, Compass provides similar results as the state-of-the-art query estimation methods. And thank you for your attention. Feel free to read our paper and visit our repository on GitHub. And if you have questions, feel free emailing us. And thank you very much.